Hi guys, this is a video over the 1-8 packet that we started last class, so please listen, follow along, and copy the notes down in your packet. So we've already talked about the intercepts, x and y, and line symmetry, and also linear or nonlinear. And remember, for the x and y intercepts, you need to interpret the answers. Like for this example at the beginning, here's our x-intercepts, where it intersects the x-axis. And that was how wide the base of the arch was, because this is the center, and here to here, this is where the arch hits the ground. And then for the y-intercept, to interpret that part, that's when you're zero distance from the center of the arch, so you're in the center of the arch, standing at the base, in the middle, and the highest point is there in the center, and that's about 630 feet. So make sure we're always interpreting the answers in the context of the problem. So you were supposed to do 2 and 3. You were working on that in class, so I'll just go over those quickly. So for number 2, the x-intercepts happen at 0 and about 5.2. So we just say the x value for that. So we would say the x-intercepts are 0 and 5.2. This point is really 0, 0, and this point is really 5.20. Now, to interpret this, we need to know what the x-axis represents. So since the x-axis represents time since opening bell, this means that for price variation, it's 0 at what times? At time 0, so at the start, and then after 5.2 hours. So the x-axis is when the y-axis is 0. So when price variation is 0, that happens at the start and after 5.2 hours. Then for the y-intercept, it's just 0. So when you have a point at 0, 0, the origin, it's an x and y-intercept. And so for this one, the y-intercept would mean when the x value is 0, so when the time starts at time 0, where is price variation, and that's at 0. So make sure you've written those two things down here. I'm not going to right now on mine. Is this linear or nonlinear? It has pieces of lines, but in general, it's not just one straight line like number 1, so it is nonlinear. And then for symmetry, we can see that this is just kind of all over the place here. There's nowhere you could draw a vertical line and fold, and the graph would lie on top of itself, so it has no symmetry. Okay, for number 3, we'll start out with symmetry or not. So this has no symmetry, because again, you cannot fold on a line and have the graph lie on top of itself. And it's also nonlinear. We can see those curves in the graph, so obviously it's not going to be a line. For the intercepts, we don't see any x-intercepts here, so for our problem, it does not have any x-intercepts. This function, though, if you looked at the whole thing from negative infinity to infinity, it really would come down here, or it could go back up. But if it came down, it would have an x-intercept, but it would be for a negative x value, which doesn't make sense for our data. So since our data is just years after 1987, we don't consider points over here. Sometimes if they show that data, we can, but in this case, we're not going to. So the only thing we have to do is the y-intercept. So that happens here at 1. So the y-intercept is 1. So what does that mean in context of the problem? It means at the start, which is in 1987, since x is years since 1987. In 1987, the price per gallon of gas was $1. And that's it for this page. Okay, on the next page, you're supposed to determine if the following graphs have line symmetry. If so, what is the equation of the line of symmetry? Draw the line of symmetry on the graph, if it has one. So for part A, we have a lawn mowing service. It's comparing time in weeks with the cumulative profit. And so symmetry, can we draw a line anywhere on the graph where if you fold it, it lies on top of itself? The answer is no. And when we have talking line symmetry, we're talking vertical lines. So no, you could not draw a line that is diagonal. So that would be considered, that doesn't count. So this one does not have any symmetry. For part B, we can see that we're comparing advertising expense in thousands with profit. And there is a line that we can draw that has symmetry. We've got this nice symmetrical curve here. And where it would have symmetry is directly down the middle. So we're going to draw this line. And I know my line's not very straight, but it's this line down the middle here. So if I were to fold on that line, this piece would match up exactly with this piece. So this has symmetry. Now for the second part, what is the equation of the line of symmetry? Remember, we talked about vertical lines being x equals lines, meaning that there's only one x value for this line, and so it wouldn't be a function by itself. So what x value are we at for that vertical line? Since we're going by 4s, and this is 8 and this is 12, then in the middle would be 10. So the equation of that line is x equals 10. When you have a vertical line, the equation will always be x equals and then whatever x value the line is at. So our answer for that one is yes, it has symmetry, and it's at the line x equals 10. Then down to the next example. These are notes that you're going to have to fill out. So we're going to talk about if a graph is positive or negative. So if I draw a graph like this, we can determine what parts of the graph are positive and negative. So the graphs that are positive lie above the x-axis. So that's this piece of the graph here, and then here, and everything above that. So make sure you write down a graph is positive when it lies above the x-axis. That's because the values are positive. The y values are positive. So not necessarily the x values, because x values are negative over here, positive over here. But the graph in general, we just say the graph is positive if the y values are positive. So that's when it lies above the x-axis. So then it makes sense that the graph is negative when it lies below the x-axis. So that'd be this piece here, going down forever, and then this little piece right here. And then on the parts where it hits the axis, those are neither positive nor negative. Those are our zeros, or x-intercepts. So make sure you write down the graph is negative when it lies below the x-axis. So in general, when we talk about positive or negative, we are talking about y values. So if the y values are negative, then the graph is negative. If the y values are positive, then the graph is positive at those points. So when we do talk about when it's positive, we want to be specific. So if I say that this x value is -5, this x value is 1, and this x value is 5, we would say that the graph is positive from an x value of -5 to 1, and from 5 to infinity. Those are the parts of the graphs where it's positive. So we already know that positive means the y value is positive, so we want to specify what x values have positive y outputs. Likewise, for the negative graph, part of the graph, we say when it's negative, what x values it's negative for. So -5 to -infinity. I'm going to abbreviate there. And so from x equals -5 to -infinity, and from x equal to 1 to 5. So we want those intervals from when it's positive or negative. So all the way over here from -infinity to 5, -5 it is negative, and from 1 to 5 it's negative. And then from -5 to 1 it's positive, and 5 to infinity it is a positive graph. Now let's turn to the next page. Now we're talking about if graphs are increasing or decreasing. So I'm going to draw that same graph. So we say a graph is increasing when it rises from left to right. So make sure you write that down. So the parts of the graph that are rising here are from here all the way up until this peak, and that's when it's going to turn direction. So after that it's not. And then here where it was dipping down, but now it's going up. So those two parts of the graph are increasing because if we read it from left to right, it's getting bigger. We're getting bigger. Here we're getting bigger. So then for a graph decreasing, a graph is decreasing when it goes down from left to right. So again, make sure you write that down. And then so for this graph, when it came to this peak here, it turned direction, so it started going down. So from there to there, the graph is decreasing, and then it starts increasing again. So for this particular graph, I've only got one piece of it that's decreasing. Now, while you see an arrow going down here, we're reading from left to right. So this is not decreasing because when we read left to right. So this is actually getting bigger as we read left to right. And that's this note I have down here. We are always read from left to right when we're talking about increasing or decreasing. And again, we're going to talk about what x values this happens between. So for this part of the graph, we're coming from negative infinity. So we say this is for the increasing part. So for increasing from negative infinity to x equal to, and I'll say that that is like -2, x equal -2, and from, and I'll say that this is 4, from x equal 4 to infinity. So those are the two intervals where it's increasing. So on your paper, for an answer, you would say the graph is increasing when, or from, negative infinity to x equals 2 and from x equals 4 to infinity. Same thing for the decreasing part. So this is decreasing from -4 to -2 to +4. So we'd say the graph, this is how you would say it on your paper, is decreasing from x equals -2 to 4. And then these parts where they dip and come to a point here, come up here and then dip, are important points we'll talk about in a second. On the one below that, we're talking about end behavior. So what is end behavior? End behavior is what's going to happen indefinitely on the left or the right side of the graph. So for this one, we are not talking about reading left to right necessarily. So for right end behavior, we're saying what is the right end of the graph doing indefinitely? Now we see if we do go from left to right that it's going up, then going down, then going up. That final going up, we don't know if it's going to come back down. If it did, this would not be a complete graph and we would want to graph it more. But since this is the only thing they gave you, this graph is going up. The very last direction it is up. So the right end behavior is up. So our definition that you need to write down is the right end behavior is what y does indefinitely as x increases. So indefinitely means forever, for the rest of the time, as x increases or approaches infinity. So what does y do? So again, as we read from left to right, for right end behavior, we read left to right. So indefinitely, it's going to increase. So we can see that the arrow is up. So this is how we're going to write it for an answer. So for this specific graph, we will say as x approaches positive infinity, so that part means we're talking about the right end behavior, y approaches positive infinity. And we also have another notation we can use on this. You can write it in words, but here's what we can do, and you'll see this in Algebra 2. As x, and then this arrow means approaches, and we would say infinity. Since there's no negative sign, we know it's positive infinity. So as x approaches infinity, y approaches in positive infinity. So if you want to shorthand it like that, as long as you know what the arrows mean, that's okay. So then for the left end behavior, our definition is what y does indefinitely as x decreases, so approaches negative infinity. And this time we read from right to left, so that's different. So now we're going backwards on the graph. So it goes down, up, and then down. That last direction is the end behavior. So it approaches negative infinity. It's going to get smaller and smaller and smaller, the y value is, as x gets smaller and smaller and smaller. So again, we're going to write it just like we did before. So as x approaches, but this time, negative infinity, y approaches negative infinity. Now it's not always going to be the same direction. We could also have a graph that is going this way. So I'm just going to draw a real quick graph. If it was going this way, then as x approaches positive infinity, this graph is pointing down. Y would approach negative infinity. And then for the right and left end behavior, as x approaches negative infinity, y would approach positive infinity. So that is an option. So it doesn't necessarily mean as if x is approaching positive infinity that y will always be approaching positive infinity. And you could also have a situation where they both approach positive infinity, like this. So the right and left end behavior are the same. That's also an option. So this shorthand version would be as x approaches, and then we just write a negative sign, and then infinity. Infinity is just a sideways 8. Y approaches negative infinity. So again, when we talk about end behavior, for the right side, we do left to right. For left end behavior, we go right to left. On to the next page. So now we're going to talk about extrema or extrema. It's usually pronounced extrema. Either one is fine. And that means extreme value. So those highs or lows, minimums and maximums. So write down the definition of relative minimum. And you just do this right on your paper. I hope you've been doing that. So relative minimum is the smallest value around a certain area. And the reason we say a certain area is, if I draw that same graph we've been using, this point right here is the smallest value around this area. So we would call that a relative minimum. And the reason it's just a relative minimum is because it's just around that area. Really, since the end behavior of this graph, the left end behavior, happens to go down to negative infinity, this graph does not have a minimum, an absolute minimum that comes next, because it goes on forever down. But this point is still really important, so we call it a relative minimum because it's where it dips and turns. It changes from decreasing to increasing. So that's another way we can write it here in your definition. So the other one is a relative maximum. So it's going to be basically the same definition, but we're now talking about the largest value around a certain area, where the graph changes from increasing to decreasing. So on this graph, that would be this point right here. We were increasing, so we're getting bigger, and then we changed to getting smaller. So for this one, again, we are reading from left to right, only left to right for these. And the same reasoning, this is just a relative minimum because it's relatively the biggest one, but the graph really goes up to positive infinity, so it's not the absolute maximum, but this is still a really important point. So for this graph, if I'd said that this is -1 and this is +2, we would say that there is a relative minimum at x equals 2 and a relative maximum at x equals -1. That's how you would say it. So I have the same little note here about increasing to decreasing, decreasing to increasing. So if we're talking about real world data, this is where you had your maximum sales for a while, minimum sales, or whatever we're talking about. So again, these are called extrema. And you can have more than one relative minimum and relative maximum in a graph. So now we'll talk about absolute maximums and absolute minimums. So for an absolute minimum, this is the smallest output on a graph. And it's still considered a relative minimum, but more specifically, it's the absolute. It's the smallest point. And I forgot to say on the last one, when we're doing minimums and maximum values, we're always talking about the y values of the graph. Always talking about the y values. So absolute minimum is the smallest point in the graph. So I'm going to draw a different type of graph here. And I'm actually going to have two graphs for this one. So for the first one, this will be for the absolute minimum. So if you look at this graph, we have some different points here. We have a relative minimum here, here, and a relative maximum here. So those are all really important points on the graph. So for the absolute minimum, I would say, or for relative minimum rather, I would say it has a relative minimum at x equals -3 and x equals 3. And then I would say more specifically, the absolute minimum is that smallest value. So over here, while they're both relative minimums, this one is the smallest because it's lower than this one. So we would say the absolute minimum is actually at x equals -3. And then for this one, this would not have an absolute maximum because it goes on forever to positive infinity on both n behaviors, but this would be an relative maximum. So I want you to draw another graph here, fit it somewhere on your paper, and I'm just going to do the same x and y axes. And then I'm going to draw that graph kind of backwards here. So the largest output on a graph, and it's still considered a relative maximum, and that is your absolute maximum. So again, we would say that they have relative maximums at, so I labeled my graph here, so at x equals -5 and x equals 4, but then you would say that the absolute maximum is at x equals 4, because that is the highest point of the graph. So again, not every graph is going to have an absolute minimum or absolute maximum, and not every graph is going to have a relative minimum or relative maximum, but they're all important points if they are there and they do exist. Okay, now we're going to do some examples with these. These were all ways that we can describe graphs, so we're going to use them to describe graphs and interpret their meanings. Okay, so we're going to start by talking about this example, kind of like we did at the beginning of the packet. So this is a health example. The outbreak of the H1N1 virus can be modeled by the function graphed at right. Estimate and interpret where the function is positive, negative, increasing, and decreasing, and the x-coordinates for any relative extrema and the n behavior of the graph. So again, when we're talking about specific points of the graph, we always want to talk about the x-coordinates. When we're talking about relative extrema, that means where are the minimums and maximums, where on the graph. So the x-coordinates are going to tell us where on the graph those mins and maxes happen. And if you don't remember, H1N1 was the swine flu. So let's do like we did yesterday. We will, or the other day, we're going to highlight parts of the graph. And if you don't have highlighters, if somebody knows where my highlighters is, you can grab them. For the first part, it wants to know when the graph is positive, and we'll say for x between 0 and 42. So that means that's our whole data that we have here. It's going to be positive, so I'll just highlight that here. All of the graph is positive in this situation. So then when we say negative, we say for no parts of the domain. And domain is important to say because really, if this graph continued, it would have some negative parts to the graph. But the domain is what we're talking about, what x values we're using, and that's for only positive days. It doesn't make sense to have negative days. So this is days since outbreak and reported cases. So again, this means that for the negative explanation, the numbers of reported cases was always positive, reasonable because a number of negative cases does not exist in our context of the situation. And then for increasing, for x between 0 and 42. So it's never not increasing. It's always increasing. And again, we are talking left to right for that. So there was never a dip in reported cases. So for decreasing, no parts of the domain because the number of reported cases continued to increase from the first day of the outbreak. So this explanation goes for the decreasing. For the relative maximum, it happens at about day 42. So it looks like it's leveling off here, so that's a relative maximum, and this is all the data we have. So while it could have gotten bigger for our data right here, the relative max at x equals 42, and the relative minimum at x equals 0. So the extrema of the graph indicate the number of reported cases peaked at around day 42. So it doesn't look like it's going to increase anymore. Then for the n behavior, as x increases, so as we go from left to right, as the days go on, y appears to approach 11,000. So what they mean there is that it's leveling off, it appears to be. If we had an arrow straight up, we would say it approached infinity. But this graph appears to be leveling out at that point. And then for the left end behavior, so as we go from left to right, it appears to be going down. So as x decreases, y decreases. And really, again, since we're not talking about negative days, we don't have to talk about it going to negative infinity. Just as we go backwards, it's decreasing. So like they say, the end behavior of the graph indicates a maximum number of reported cases of 11,000. Now we'll go to the next page. Okay, for this last page, we're going to estimate and interpret where the function is positive, negative, increasing, decreasing, x-coordinate of any relative extrema, and the end behavior of the graph. So we need to make sure we interpret each of these as well. So these are the three examples we had on the first page. So starting with the first one, we're talking about that right whale population. And for positive, the graph is positive for all parts of the domain. So from x equals 0 to x equals 10, because those are the only x values in our domain. To interpret that, that means that the population was always a positive number or 0. So we've always had some whales or 0 whales. You can't have negative whales. Then we would say, since it's always positive, the function is never negative. So the function is negative for no parts of the domain. There were never a negative number of whales. So if you can't remember this exact wording, no parts of the domain, you can say for our data, for this graph. For increasing, we can say that we're never increasing. So we say that the function is increasing for no parts of the domain, so the population never increased, it never got better. So we would say the function is decreasing for all parts of the domain, so that's from x equals 0 to x equals 10, and this means the right whale population has continued to decrease. All right, x-coordinate of any relative extrema. So we can see that there is a maximum here, so we'll call it a relative maximum, because if you graph this whole line, it would go up forever, but we're just talking about this, so there's a relative maximum, and you could call it absolute, at x equals 0, and this was not supposed to be it means means, so it means that the biggest number of right whales in recent history was about 250. And then a relative minimum would be at x equals 10, which means after about 10 generations the right whales will be extinct. And last thing to describe about this graph is the end behavior. So as x increases, y decreases, and that again means that as time goes on, the population is decreasing. And then for left end behavior, as we go backwards, it is increasing, which means we had a higher population before. On your homework, feel free when you have to describe graphs like this that you can type them up, as long as I want you to print them out for me or submit it on Shobi. Okay, for number 2, the stock price, we can talk about the function being positive. So it is positive. Here it's 0, that doesn't count as positive, then it's negative, and now it's positive. So the function is positive from x equals, I said 5.2 on. So I'm going to say to x equals 7 because that's where it appears to stop. But the arrow does indicate it keeps going, even though here it's not going to go negative. So you can either argue from 5.2 on or from 5.2 to 7, wherever the graph ends. So this means the price variation, that's your y value, was positive, which means an increase in price for the stock after 5.2 hours after the start. So then the graph was negative between 0 and 5.2. So that means, so we would say the function is negative from 0 to x equals 0 to x equals 5.2, and this means that the price variation was negative, so that means decreases in price from the start until 5.2 hours after the opening bell. So just because I said decreases in price, I'm talking about from the start. So you can see here that this piece is increasing. That's not what I'm talking about. It's still a decrease. These numbers all represent smaller prices than at the start, which was when the price variation was 0. So the price was dropped and it's still below what they started, even though it's increasing here. And then above the x-axis means it's selling for more than they started. So we would say the function is increasing from x equals 3 to x equals 6. From here to here, it's increasing. And that means the price of the stock got better, starting at 3 hours up until 6 hours. So it got better from what it was previously. Again, the starting point is here, so it's depending how you're talking. Here, the price of the stock from the start wasn't increasing, but it was increasing from where it was. So you could say that. It's increasing from x equals 3 to x equals 6. So for the function is decreasing, it's at those other times. So the function is decreasing from x equals 0 to x equals 3, and this means the stock continued to get smaller during the first few hours, during the first 3 hours. Then for our extrema, there is a relative maximum at x equals 6 because it's the highest point here on the graph, and this means the stock's highest value is after 6 hours. We don't know exactly how much that was because they didn't tell us the original price. This is just in points anyway, but it doesn't tell us the original point value of the stock in the first place. We just know that that's its highest point in the graph. And the last part I had to put over here, so the relative minimum at x equals 3, and this, so right here, that means that the stock's lowest price occurred at 3 hours in, so after 3 hours after the opening bell. And then for the end behavior, we can see that as x increases, y is going to approach about a half a point. So again, we don't know the actual price, but a half a point. And for the left end behavior, it's approaching 0. I'm going to go ahead and delete all these so that I have room for the other one. So for our last one, again, average price of gasoline. So we will talk about first positive and negative. So the graph is positive for all values of x. So we say the function is positive for all values of the domain from x equals 0 to x equals 25, and this means that gas was never free. And then the function is negative for no values of x, so this means that there was never a negative price for gas, which makes sense. For the function increasing, this one's kind of hard to see, but there is a little part that's like a maximum here and a minimum here. So I'm going to say that the graph is increasing from about x equals 0 to about x equals 4, and then again from x equals 10 until x equals 25, and you could say forever after that. And this means that the price of gasoline increased from 1987, because this is years since 1987. So the price increased from 1987 to 1991, and then again from 2000, or from 1997 until 2012. So then the other part of the graph is decreasing. So the function is decreasing for x equal to 4 to x equal to 10, and this means the price of gas decreased from 1991 to 1997. So I'll go ahead and highlight that part of the graph like that. And then for any relative minimums and relative maximums, we can see that there's going to be a relative maximum here because it changed from increasing to decreasing. So relative maximum at x equals 4, and so this means that gas prices peaked in 1991. So it had been the highest the gas had ever been in 1991, but then it went down. So they thought that was the highest price they'd ever see again, and then nope. And so then for a relative minimum, there's a relative minimum at x equals 10. Again, we can see that because it changed from decreasing to increasing, so that's got to be a relative minimum. It didn't get smaller again, it got bigger. And so this means that the gas prices hit a new low in 1997. So it was a new low because it was the lowest they'd been, and then it continued to increase from then. And you could even call this, this is really, it's hard to say, especially since I've written on it now, but you could call it an absolute minimum, but absolute minimum here for our data was $1, but we know that the average price of gasoline before then was less than $1. And then for the end behavior, we can see that as x increases, y increases, so it's going to get more than $6, and then it's going to continue to increase, but we know that it's gone up and down and up and down. That's what it usually does, but this is average. And then as x gets smaller, then y decreases as well. Okay, that's it for the top half. Now we're going to do a bigger graph with more involved in it. Okay, instead of typing all this out, I'm just going to talk through it. Okay, so make sure you're writing this down. You can pause it. So used retail sales of video games from 2000 to 2009 can be modeled by the function graph to write, estimate, and interpret where the function is positive, negative, increasing, decreasing, x coordinates of any relative extrema, and behavior. So same thing we were doing above. So first of all, for positive, the graph is positive from x equal to negative 0.75 to x equal to 10 and a half almost. And so that means that from before 2000 until 2010, mid 2010, there were video game sales. So when is the graph negative? The graph is negative from negative infinity up until about negative 0.75. So from a little bit before 2000 till, all the time before that, there were negative video game sales. And from 2010 on, there's negative video game sales. So that doesn't really make sense. So we don't really need to include that in our interpretation of the graph, because realistically we know we cannot have negative sales. And by 2010, we know that we're not going to have this low of video game sales to where it needs to go to negative video game sales. Then where is the graph increasing? So the graph is increasing from x values from really negative infinity, but if we're talking just where it makes sense, from x equals 0 until about x equals 1.5. And then again from about, we'll say, just go ahead and say 3 until x equals 8. So from x equals 0 to x equals 1.5 and x equals 3 to x equals 8, the graph is increasing. So that means that during those times, so from 2000 to about mid-2001, and from 2003 till 2008, we saw increases in video game sales. On the other end, we're talking about decreases in sales. That happens from about mid-2001 until 2003, and then from 2008 on, or until mid-2010, we saw decreases in sales. That means we were losing sales. Well, decreasing in sales. Okay, let's talk about relative minimum maximums. Anytime there is a switch from increasing to decreasing or decreasing to increasing, we have those relative extrema. So here is a relative maximum and here is a relative maximum. So there's a relative maximum at about x equals 1.5 and x equals 8. So that means the video game sales peaked mid-2001 and in 2008. And you could call this an absolute maximum. That was the most that video game sales had ever been. Then for our relative minimum, there's only one here. So we can say that the video game sales hit a low in 2003. So that's the lowest they'd ever been in a while. And then for the end behavior, since we have other parts of the graph, we can talk in general. As x increases, y decreases. As x decreases, y decreases. So I'll go ahead and write that one out. So as x approaches infinity, y approaches negative infinity, and so that's your right end behavior. And then your left end behavior, as x approaches negative infinity, y approaches negative infinity. So this is one of those graphs where y approaches negative infinity on both sides. So as time goes on, we're going to negative infinity. If we go backwards in time, it approaches negative infinity. And again, in this situation, the end behavior doesn't really help because we know that sales are not going to get to the negatives, and then they weren't in the negatives before 2000. Okay, that's it for the packet. For your homework, you need to do the worksheet for 1-8. So it's actually called Worksheet for Homework 9 over 1-8. And that is on Shobi, and I'll have the sub give it to you on paper too. But that's your homework, and it has 4 problems on it. It's doing the exact same thing we were doing on this last page, the last 4 examples. And again, you can type up your explanations, and I'd rather you do that and print them out so that you can have a long explanation and really interpret the answer, because I know you guys don't like to write and it gets annoying, and it's easier if you just type it up. So I would like you to do that, please. And that is due on Wednesday. I will also be checking your packet to see that you wrote down what we did today here in this video. Thanks, and I'll see you on Wednesday.